going on, Network Ninjas? This is CBax coming to you with another video. I just wanted to bring up a topic with you guys. For any of the network engineers who are starting to do a transition of or let me say not even transition, but incorporating more scripting and programming into your daily activities, or you're playing with it and you just wanted to learn some new things about programming. Well, this is something that as my scripts have started to grow into more applications, there's certain things that have become very slow in operation, and one of those things is searches, especially when I'm dealing with like huge chunks of data and dealing with IP addresses or something like that. If I'm looking for a particular IP in that range, it was taking a long time because I was doing a very linear search style. So I decided to start doing some research. And one of the things that I've been doing in this past few weeks has been looking at like some computer science theory, just so I can start getting a better grasping a better understanding of how programmers think and solve certain issues. Um, and a part of my discovery, one of the topics that I came across was binary searches. Um, there's a bunch of different search methods, or if you start getting into data structures, traversal methods. But in this particular case, I'm not going to go into any of that because I'm nowhere near as competent to talk about that stuff as I think I should be. Um, so with this particular topic, this is really addressing for searching. Now, me being a network engineer and all the practical examples that I was reading, it was very heavy on the computer science stuff, which it definitely should be. So I was able to grasp the concept, but I couldn't really see it in a practical application. So that's what I'm planning on doing with this video, is show you guys some binary searches from a network engineer's perspective. But then in the first half of this, we're just going to go over um, the theory behind how this works. So we start my presentation here. So binary searches with Python for network engineers. So the two methods that were more common, the most common method that we know is linear searches. If we look at the time constraint, it's big O of n, which means that each item in that list, n representing each item in the list. So if I have a list of 1,000 values and I'm searching for a value, I technically have 1,000 values that I need to search to in order to find that value. Now, if that value is in the beginning of the list, it's not a big deal. I can find it rather quickly. But if the value is towards the end of the list, you can see how long that can take a couple seconds or minutes, depending on how big the data set that you're working with. It's the most common search method for the linear approach. If you've written Python code before, it's your standard for loop, for I in list. Match this or equal, value target equal I or whatever, and then you have a match if you return that value. So that's what we're normally used to doing, is that we're going to inspect every specific item in that list. Well, particularly me as a network engineer, I start dealing with some higher, let me say, subnets. When I'm dealing with subnets and I'm dealing with higher CIDR or lower CIDR notation subnets, you start getting bigger ranges of IP addresses that you have to funnel through, especially once you start dealing in the Class B and Class A realm. Um, you start you start having to go through a couple million IP addresses, depending on the network that you're in. So that was the issue that I started running into. With binary searches, the time constraint is big O log of n, um, which means that we're going to be finding the median of that particular list. So I'll go through how that all works, but not as common. It's much faster when searching high density arrays. And I say not as common for a network engineer's perspective. It's not something that we would learn in, because typically this is very computer science heavy. You see data scientists doing stuff like this, but it can definitely be incorporated with stuff that we're working on. And the way it worked is it searches by comparing the value of the midpoint index to the value in the array to the target that you're looking for. And it may sound kind of foreign now, but when I go into the code demonstrations, we'll go through and show you guys how that works. So execution. So what we need to do, there's a few steps that has to happen. So one of the main things about ordered lists, and I think I looked over there, is that the array must be sorted. If it's not sorted, this will not work, because you're not actually searching based off of the values in the list. You're searching based off of the midpoint index value of the list. And if that midpoint index is out of order, you typically would have bad. You're not going to get good results because of the way the binary method actually works, as it shrinks and grows the list as needed to search. So execution. So the two main things that we got to do first is that we need to identify the lower half of the index and the upper half of the index. So the lower half of the index is always going to be 0. Python starts with 0 index list, so it's always going to be 0. And then to get the upper half of the list, what you want to do is take the length of that list and negative subtract it by 1, and that'll give you the top end of the list, whatever the top index of that list is. Now, what you're gonna have to do then is that while the lower end of the list and is less than the upper bound end of the list, you need to calculate the midpoint index of the list. And the way you do that is that you want to take the lower bound plus the upper bound, and you need to divide it by 2. And in this particular case, we're going to do floor division. Reason being is that if we do normal division, we'll end up getting remainders. And if you ever try to do a Python lookup on a list with a decimal point, you'll know that it'll throw errors. So that's one of the reasons why we need to use floor division. It'll strip that remainder off and only take the whole number, thus giving us our index position of whatever the midpoint should be. Now, if the midpoint value is less than the target value, what'll happen now is that first we're going to check it now if that midpoint that we just calculated, if it's equal to the target, then we're done. Everything stops there. In a perfect world, that's awesome, but in this particular case, we're going to have to go through and do some additional logic if that midpoint does not match. So what will happen is that if the midpoint value is less than the target value, the lower bound index must change, shifting the list to the right. So what ends up happening is that if I go through and I do my check and I say, okay, well, I take that, now that I get my midpoint index here, I need to take that index number, put it into that list or reference it in that list and get the value out. And I compare the value. If that value is greater or less than, if that value is less than, that target value is less than, well, let me say, I'm sorry, if the midpoint value is less than the target value, we need to shift the lower bound index, meaning the lower bound that we set to 0 needs to shift up to the midpoint, and then we need to add 1 to skip over that midpoint. Same thing goes if the midpoint value is greater than the target value, the upper bound index must change, shifting the midpoint, the upper bound position to the midpoint, and then minusing 1 to skip over that midpoint. Now you want to repeat this step until the midpoint is matched and to the target, and then you'll go and have your result. So it sounds super confusing. I think it took me a while for me to grasp that, but once you run through it a couple of times, it'll really start to stick. But that's the basis of how this works. So let's go ahead and look at a diagram that I put together for you guys. And what's going to happen here is that we have a list of 6 items. They're already in order, as you can see here, and we're indexed from 0, 1, 2, 3, 4, 5, 5. Technically 6 items, but because of the 0 index. So in this particular case, what I'm going to do is I'm going to look for the number of 100. Now, in a normal lookup, I would have to do for a linear approach. I would have to say, okay, 6, are you 100? Nope. 7, are you 100? Nope. 45, are you 100? Nope. 100, are you 100? Yes, you are. Match. And that's how we would do a linear scan. So this is not that big of a deal because it's only 6 items. But if that list was, say, 1,000,000 and 100 was in position 1,000,000, you know how that can take a little bit of time. So with this binary search, we're going to go ahead and walk through what a binary search looks like. So if I go through and I want to first set my lower bound and my upper bound index. So as we already know, the lower bound is always going to be at position 0 for the start, and then the upper bound, what I'm going to do is I'm going to take the length of the list, which is 6, divided by -1, which would give me the number 5, and that would be the upper bound part of my list, right? So then what we have to do now is calculate the midpoint. Now in order to calculate the midpoint, what you have to do is add 5 and 0 together, which would give us 5 divided by 2, which would give us 2.5, I believe. But then if you go to, but if you take that whole number, you get 2, which now 45 would be our midpoint. So we go ahead and do our first comparison. Is 100 equal to 45? Obviously it's not. So we'll move over to the next. So since the midpoint value is less than the target, remember it's less than the target value, we want to shift the index to the we want to shift the lower bound index to the right of the mid index. So what that means is that L will now move over to 2 plus 1 would give us 3. So now our new or low bound is going to be 3, and then our upper bound is going to be 5. We have to recalculate that upper bound again, that midpoint again. So it would be 3 plus 5, which is 8, divided by 2, which gives us 4. So our new midpoint is 154. Now, we compare the values again. I say 154 is not equal to 100, obviously, but we see that 154 is greater than 100. So what we're going to do is we need to shift the upper bound index to the left of the mid index, and that should be, our previous mid index was 4. So we need to do 4 minus 1, which would give us 3, as you can see here. So now the lower bound and upper bound match, and the midpoint is on the same point. And the third index is 3, and value is 100. So we go to compare those values, we see that 100 is equal to 100. Now, it may look like that was a lot more work than a linear search, because it took me a second to really get what was going on there. But in this process, what we did was we took a search that would have took 4 steps, 1, 2, 3, 4, if I was to do this in a linear fashion, and we turned it into 3 steps. And we skipped over 7, and we skipped over 200. We never even had to look at those numbers as far as memory is concerned. So that did a huge deal for us on performance from a memory perspective and a speed perspective because of our attempting this. Now, we're going to go to the code, and I'm going to show you guys the code in a few different lights. One of those is going to be, first, let me go ahead and clear this off here. Clear that out. I can close this out. So hopefully you guys can read this okay. So I'm going to go through and we're going to look at all the functions that I created for this example. And then I'll show you the data types, the different tests that we wrote to go ahead and test this out. So first we're going to start with our binary, we're going to look at our linear function first. So this is our linear search function. If we look at that, another thing that I did too is because I wanted to get the timing, I wanted to show you guys the execution time. I have some calculations going on for execution time, so that's why you see this start and end here, and then this calculation happening at the end. But what we're going to do is we're going to look for num and I, because I'm using the enumerate function, so it actually gives me the index position. And I'm just going to do, like I said, the standard for loop for I and list, which would be the list that I'm passing in. If I equals target, then I'm done. And that's a linear approach, very easy, quick code, straight to the point. Now, let's look at our binary search function. So the binary function is a little bit more, and ignore the print statements as well. I did this because when I run the code, I want you guys to see what's happening along the way, so it just makes it a little easier. So the print statements are just extra, but I'll also have this on GitHub if you guys are interested in it. You can go ahead and take a look at the code yourself and give this a shot. But the binary search is going to take the array, and it's going to take the target value, right? Same thing, I'm going to do the start time here. I'm going to do an edge case check to make sure that if it's not the array or if the length of the array is 0, I'm going to return false because I don't need to do any work if the array is empty. Now I'm going to set my lower index to 0 like I said earlier, and then I'm going to set my upper index to the length of the array minus 1. In this particular case, I'm just going to print the target value. I'm going to say the target value is whatever I passed in here. Now, beginning my while loop, I'm going to say if my lower index is less than or equal to my upper index, which would start the loop here, I'm going to say mid index equals lower index plus upper index divided by 2, which gives us my midpoint index. And I'm going to print that out. I'm going to say my lower is my lower index, my upper is my upper index, and I'm going to print my mid index here. Now, I'm going to need to grab that value, that mid value, after calculating that mid index. So I'm going to say mid value is the array, and I'm going to index for that particular mid index, and I'm going to print the mid value out. Now I'm going to do my conditional checks here and say, okay, if the mid value is equal to the target value, I'm going to end time, and I'm going to return true the calculation of my execution time and the length of the array, so how big the array was. Else, if the mid value is less than the target value, I need to change my lower index, which would be mid index plus 1, which would shift it to the right. If I do my upper index, it would be if it's greater than, what I'm going to do is shift my upper index, which equals mid index minus 1, which shifts it to the left. And then it'll print the new upper index as well. Got my end time and then start, and this only happens if I don't make a match. So this return false here at the bottom outside of this loop will be a return false and a calculation to show that there was nothing in that list that I needed. Now, we're going to go ahead and do a test demo first. I'm going to show you the demo that we had in the example there, and then we're going to search for 100. So let's go ahead and comment that out, and we'll do a test demo. So in this function, all I'm doing is I'm creating that test list here. And then if method is bin, and because I'm calling that test demo function from my main function, I'm going to pass the bin is the first parameter to say run the bin binary method, and then we're going to run the binary test. So let's take a look at what happened. So when I run this, off to the side here, if we look at, we say the target's 100. We say the first lower index is 0, the upper index is 5. Now if we attribute that back to our diagram there, we notice that we said that earlier, 100, 0 and 5. Now, if we go back and we say, okay, so our mid value is 45, which is true because the mid index should be 2, right? Now, we're going to do our first check. We said that it's not equal, and we see that 45 is less than 100, so we're going to change our let's see, 45 is less than 100, so we want to change our lower index, so our new lower index is going to be 3 based off of the calculation as we've seen here. So our new lower index is 3. Now our lower is 3, our upper is 5, our mid index is now 4, and the mid value of 4 in the 4 position is 154 as we've seen here. And then because 154 is greater than the 100, we need to change the upper index now, which it's now going to be 3. So our new upper index is going to be 3, and then our lower index is 3, and our mid value is now 3 because 3 plus 3 is 6 divided by 2 is 3, which gives us the mid index is 3, which now you can see that we got a match. It took what is it, a nanosecond or a microsecond, I never could get that right, to execute, and then the length of the list was 6. That's great, works awesome. Now let's see what this looks like in a linear fashion. Now, in a linear fashion, I think this is the microseconds, so that was a lot faster than the binary function, the binary fashion of searching, so this might not have been as needed, but I'm going to show you guys what it looks like to do it with a large IP address set. So if I do the bin test, and I have a one for test IP, I have a function for a test IP. So what I did here is I'm actually using this package called IPCalc. If you don't already have it, it's a part of the standard. It's not a part of the standard library. It's available on pip. You can install it, pip install IPCalc, and what it is, it's a library that was created to handle IP addresses, IPv4 and IPv6. It can do conversions. It can give you MAC mappings if you want to do something to make a MAC address that maps to the IP address. It can give you a conversion from hexadecimal to binary to decimal. It's a really awesome, powerful, lightweight package that really helps me out with dealing with IP addresses, so I use it for everything. And the best thing about it is that it creates an object, a network object, that all I have to do is pass a CIDR, a subnet, and it will create that, and then I can cast a list over it and get all those IP addresses inside of that subnet. So it just makes it really easy to deal with. So that's the package that I'm using in this particular case. Now, first I want to create a variable called my IP, which I'm going to pass the IP address that I passed into the function into this IP class. Then I'm going to create a network class, which would be a subnet, and I'm going to use a /12, which should give me a little bit more than 1 million addresses. We'll see here in a second. And then we're going to create out of that network object, we're going to cast a list. We're going to make it a list and make that a net list. And then we're going to pass that net list and my IP into the bin search or linear search based off of the type of search that I want to do. Now, first, let's go ahead and do it with a linear search to show you guys. So in a linear search, what I have it doing is I have it searching each value in the list. It takes a little second to spin up to create the list. I don't have that associated in the calculations, but as you can see here, I went through 100,000 entries before finding my target, which was 140.2. Now that is 101,377. So you see we got a match. It took 2.5 seconds to find that inside that list. And the total number of IP addresses is 1,048,574 that we have in that list of search through. So it took 2 seconds to do that, which yeah, depending on what your appetite is for processing, and if if it doesn't take that long for you, if that's not that bad. But for me, that's kind of horrible, especially if I'm doing a couple of hundred queries a day. 2.5 times 100 can quickly escalate to a higher processing time, which can cut down in productivity. So, and user experience too. If you wrote an application and it's a web app and the users are waiting, 2 or 3 seconds for a response back, that's not going to be good. So that's what happens in the linear approach. Now let's check this out and see what happens in the binary approach. So with the binary approach, same thing, same IP address, same subnet. We're just going to go ahead and run it. I don't have the calculation, like I said, of it creating the list because that does take a chunk of memory, that it takes a little time. But as you can see, the execution was significantly faster. Now, if we start at the top here, we can see that our target was indicated here. Our lower is 0. Our upper is the 1,448,573 because we did a -1, I believe. Yep. And that gives us our top half. And then we start going through and we make our matches. And you start seeing the changes in how the upper and lower is starting to shift. So right now, the lower end of it is shifting. It's shifting down, and then we have the lower shifting up to match up to get it back to the median until we eventually land on our mid index, our mid value, which is 10.140.10.1.140.2. Now, that seemed like a lot, but I just wanted to do a quick math calculation for you guys. So what ends up happening is that we end up skipping all those values between the upper and lower. So the first change was the upper index got shifted. So we're going to go for 1,048,573. We're going to subtract that from 524,285. Now, in that particular case, we skipped over 500,000 values that we potentially would have had to search through in order to find this IP address, which is freaking awesome in my opinion. I mean, that's a huge savings in memory. You don't have to have all that stuff sitting in data and memory eating up resources. So this search pattern, as like I said, this is applied with binary searches and searching for IP addresses. This is just the start of it. I mean, I have some ideas about creating a config parser that can search through this, but I think we're going to have to end up doing binary search trees, but that's a whole other topic. But you can see the savings are substantial. I'll show you guys another demo that I did for this, is that the binary of a test of doing a test integer. So I created another function here. What it does is it creates a list based off of the range of a million, I think 10 million. You can see how many of the numbers that is. So that's 10 million, I think. Yeah, 10 million numbers. So the list is 10 million, and then I add 3 to give it a little bit of variance there. So what I'm going to do is going to dynamically create this list in memory, and then it'll go through and search for my number in that list. And I did this number high enough that you guys can actually see the benefit. So if I go through and I say linear and run this, it's going to go through all those numbers, and it took 1 second to search through and get 66,656, right? 10 million entries, 1.3 seconds. Now let's see what this looks like doing a binary search. I mean, that is just amazing. Same number, same data structure, same amount of data inside, but the amount of time that it took was significantly less. And doing this binary approach, I was able to get to my mid index and getting my value and making that match rather quickly. So um, I I hope you guys enjoyed this. I thought this was really beneficial. I really liked learning about this. This is a really cool topic for me to get into. So if you guys have any questions, if you want to see more examples, let me know. I'll post the link to GitHub for the code down into the comments. You're more than welcome to fork it, improve it, change it, implement it. And what's really cool about this is that you see me deal with two different data types at this point. I did with integers, I did it with strings. It will match, it will work with anything. The biggest thing is that the list must be sorted. Um, so if that prerequisite is met, binary searches will work. Now, depending on your use case, it may not be as beneficial as we saw with the first demo, looking for 100, looking for that number 100. It went faster doing a linear approach, so you know you got to learn to assess the situation and pick out the right solution. It's just like engineering. You guys are looking at a site and you're deciding to use OSPF over EIGRP. If I'm doing an MPLS TE setup, I'm definitely going to use OSPF. If I'm going to be doing a DMVPN setup, I'm going to use EIGRP. So it's just situations like that. You got to decide what's best for the scenario, what's best for the solution, and if it makes sense. Because if it doesn't make sense, it don't make money. If that makes sense. Sorry, that was corny, but whatever. But I hope you guys enjoyed it. Please leave any comments or questions if you have any. Later.